Hi everyone. So I'm Sandeep Kumar Acharya. I'm a postdoc at University of Manchester. So I'm going to talk about importance of soft photon heating for 21 centimeter cosmology. So 21 centimeter over 1.4 gigahertz line arises from hyperplane splitting of ground state of hydrogen. So the observable that we are looking at is basically the distortion temperature, which is delta TB, and this is proportional to the difference between what is called the spin temperature of neutral hydrogen and the radiation temperature TR. So typically in literature, TR is assumed to be equal to the CMB. But if you have some extra radiation from, say, exotic sources like dark matter decay, then the TR can have extra contribution. So then we have to replace TR as TCMB plus some delta T, where delta T is contribution coming from other sources. So the spin temperature is defined as the ratio of population of upper and lower hyperplane state, which is given by this equation. So spin temperature depends upon astrophysical modeling, such as, and depends upon various astrophysical processes, such as interaction of neutral hydrogen with radiation, collision with hydrogen atoms, electrons and protons, Lyman alpha photon scattering, and also X-ray heating from energetic photon sources. And the spin temperature is given by the weighted sum of radiation temperature, matter temperature, and color temperature of the Lyman alpha radiation field. It is typically assumed that Lyman alpha color temperature is equal to the matter temperature. So recently, a strong 21 centimeter absorption signal was reported by HS collaboration with delta TB of magnitude 500 millikelvin at redshift of 18. Typically, with just CMB as background, we expect delta TB of the order of 100 to 150 millikelvin with the uncertainty coming from astrophysical modeling. So this absorption depth can be explained by extra radio background on top of CMB because the delta TB is proportional to the difference between radiation temperature divided by spin temperature, as long as the spin temperature does not get affected by the radio background. However, I should point out that the edges measurement could not be reproduced by a recent experiment called SAROS. So this measurement is still in contention. So in this work, we use edges as a figure of merit, and we do not claim that this is a proper detection yet as of yet. So there is another experiment called Arcade, which has detected excess radio background, which is seen as today. So they measure radio monopole on top of CMB within 20 megahertz to 10 gigahertz, and this observation was corroborated by another group using the data from LWA. So in the right hand side figure, I'm showing the excess temperature as a function of frequency. This radio background can come from actual astrophysical sources, but even after we account for resolved discrete radio sources that we know of, we still cannot explain this radio excess. And we can fit this radio excess with a power law with a spectral index of minus 2.6. So once we it is natural to link these two radio excess. So if you assume that this arcade excess was already present at redshift of 20, so we can ask the question, what should be the consequences for edges detection? So if you assume that the arcade excess was already present at redshift of 20 and afterwards it just redshifted to today, the absorption depth that would have the absorption depth that the edges would have detected would be like 3 times higher than what they have observed. So this edge detection allows only about 5 to 10% of this arcade radio access at redshift of 20. I should point out that 21 centimeter anisotropy measurement can also put complementary constraint, because with 21 centimeter anisotropy, you are measuring the temperature contrast. So let's say you have a hot object and with a cold background. So if the difference between the contrast between the two background with respect to source is higher, then you can easily detect detect this constant contrast. So by this method, we can constant what should be the temperature of the background. So the recently Hera collaboration has put some constant on this background at ratio 10, but they still don't allow or exclude the edges detection as of yet. And with all these constraints, there is a caveat that they have assumed that these radio photons only once injected, they just redshift. They do not take part in thermalization in this at this redshift. So there is a big literature on the evolution of photon injection evolution of photon injection and thermal history of the universe. So in this plot, I'm showing what I'm computing is basically CMB spectral distortion from injection of monochromatic photons. So the CMB spectrum is in equilibrium with electrons and is given by Planck spectrum. But once you inject some photon, we disturb this equilibrium. So the photons and CMB photons and the electrons will try to achieve a new equilibrium, but the universe is expanding underneath them. So the equilibrium process is not complete, and we see some the features of non-equilibrium process, and this can be observed today by multi-frequency CMB experiment. So in these plots, I'm in the left-hand side plot, I'm injecting photons at a frequency, at one particular frequency, and at one particular redshift, and the redshift is basically denoted by these numbers. And as you can see, the spectral distortion shape, which is the difference between the CMB spectrum as seen today with respect to the Planck spectrum. So basically, this is a function of injection redshift, and also these can be function of photon spectrum. So at the right hand side, so these cases are for two different photon energies. So we can consistently solve for this evolution of thermal history of the universe using a code called CosmoTherm. We can compute CMB spectral distortion, temperature evolution, ionization history, and even 21st century global distortion signal. And we have added modules to analyze one energetic photons, broad photon spectrum, and even string decay recently. So since we are interested in injecting broad spectrum of photons, let me distinguish between what is called hard photons and soft photons. So any photons with energy greater than 13.6 eV, which is the ionization threshold of neutral hydrogen, we call that the hard photons. So these can ionize the neutral gas in post-recombination universe where you have neutral hydrogen. And this can lead to strong CMB anisotropy constraints. So because you have more number of free electrons, the CMB photons can scatter with them, which basically homogenize the CMB anisotropy. So that will damp the CMB anisotropy, and one can constrain them with Planck observation. So if you have photons with less than 13.6 eV, so they cannot directly ionize the gas, but they can be absorbed by the free electrons by a process called by free absorption by Bremsstrahlung. So the energy of the photons, absorbed photons, will go into heating the electrons. That will raise the gas temperature. That can also change the post-recombination ionization history, because the recombination coefficient between the electrons and the neutral hydrogen is a function of temperature. So once you change the temperature, you can actually change the recombination history. So therefore, there is a possibility to change the post-recombination history in this case as well. So in this slide, I want to show the complementarity between CMB and 21 centimeter observable for hard photon injection. So in the left-hand side plot, so in this paper, the authors have studied the effect of matter accretion on primordial black holes. So these primordial black holes, after accreting the material, can radiate radio photons. And these authors showed that the flux of radio photons can explain these arcade axis. But typically, astrophysical emission have broad emission spectrum, so these black holes can also emit UV photons. And the flux of UV photons is correlated with the radio flux because the process is basically same, which is the black holes accreting matter. So what we did is basically we took the UV photon flux and computed the amount of ionization that it can do to post-recombination universe, and which is plotted in the right hand side figure. So as you see, there is a drastic change in the ionization history, and this can be strongly constrained by CMB anisotropy experiment. So there is a complementarity between the 21 centimeter and CMB absorption, 21 centimeter and CMB observables. So next I shift to the soft photons. So as I said, the soft photons cannot directly ionize the neutral hydrogen, but they can hit the electron by being absorbed by these free electrons by a process called Bremsstrahlung. So in the figure, I'm showing the optical depth as a function of redshift. So as you see at redshift beyond 1000, the optical depth is much higher because the density of the universe is much larger and the photons and electrons are strongly coupled. But once the recombination happens, basically photons and electrons decouple, the optical depth is much lower, but it is a frequency dependent term. So as I reduce the frequency, I can reach an optical depth of 1, say at frequency say 10 to the power -4 or 10 to the -5. And this absorption will lead to electron hitting. So to study the effect of short photon injection, we consider a phenomenological model, which is like a decaying profile with a lifetime of tau, with inverse lifetime of tau. And we inject a photon with a broad spectrum, which is a power law distribution with a cutoff. And we consider two cases, which is free and symphoton spectrum. So the qualitative results that I am going to show is independent of this model, but we have used this model to have better control over the calculation. And so this plot basically summarizes the qualitative features of our work. So here I'm showing the radiation temperature, evolution of radiation temperature, matter temperature, and spin temperature as a function of redshift. In black, I'm showing the standard cosmology case. In red, with including the short photon heating effect, and in blue, without including the short photon effect. So as you can see, the with inclusion of short photon heating effect, the matter temperature is boosted, even at redshift of let's say 100, and it gets a severe boost at around redshift of 20. So this is where basically reionization happens. So once you have more number of free electrons, these short photons can be absorbed more efficiently. That's why you get a large boost. So if you have neglected this heating effect, then basically the matter temperature evolution is basically same as the in standard cosmology. But so this changes the spin temperature evolution drastically. So in red, basically with inclusion of short photon heating, and in blue you can see the spin temperature without short photon heating. So there is a large change in. So this will have a strong implication for 21 centimeter global signal. So here I am plotting this 21 centimeter distortion signal as a function of redshift. So as you have seen from the last slide, without inclusion of short photon heating, we get this blue curve. And I should point out that this is scaled by a factor of 1/3. So basically, this will be in tension with the edges detection. So the green point is basically the edges detection point, and basically these two will be in tension with each other. But with inclusion of the heating effect, the red one basically that is consistent with the edges detection. So, yeah, and once again we can have complementarity between 21 centimeter and CMB observables. Basically, this heating will lead to a change in recombination history, as I saw in the right hand side of figure, which can be constrained by CMB anisotropy. So you can basically constrain your parameter space of the model using both CMB and 21 centimeter observables. And this heating mechanism is only effective in post recombination universe, because if you have injected photons in before recombination, because the photons and electrons are so strongly coupled that these soft photons will be absorbed before recombination itself. So there will be no more photons, soft photons available at rate of 20 where you need it to hit the medium. So basically that's what you are seeing in the left hand side figure, that there are photons missing in this part of the spectrum if I inject photons at very high rate shift. And then the 21 centimeter observation, you see that there is a big absorption depth which will be intensive with the J detection. And this heating mechanism is dependent on soft photon spectrum. So here I'm comparing two cases with free and synchrotron type spectrum. For a free type spectrum, which is in blue, there are less number of photons in this part of there are less number of soft photons. So the heating will be also less effective. So then the absorption depth will be much bigger, which is shown in this blue. One can also compute this heating effect for a more physical model. So in this plot, I'm showing one particular case for a string loops decay, and the reader can find more details in this decay. Until now, I have discussed about the effect of soft photon heating for 21 centimeter global observable, but this can impact 21 centimeter anisotropy as well, because as I have said, you are with 21 centimeter anisotropy, you are measuring the temperature contrast between hot object on a cold background or vice versa. So if you have more, if you have a colder background, you have more contrast, and you can the power spectrum will be much boosted. So in this plot, I'm showing the power spectrum as a function of redshift for a particular length scale. So in black, I am showing the standard prediction, standard cosmology prediction, and with red, with addition of radio background, but without including the soft photon heating effect. So you see there is a large boost from the standard cosmology case. But once I added the heating effect, basically that reduces the contrast, and that basically um, that you can see in this figure that the difference between the two cases, that is the red and blue one, is like order of magnitude. So you have to take this into account to get to constrain these kind of models from even 21 centimeter anisotropy. So these are my conclusions, and thanks for your attention.